Welcome. We are on page 2 of the Chapter 4 exam practice and number 9. A student ran out of time on a multiple choice exam and randomly guessed the answers for the last 2 problems. Each problem had 5 answer choices, A, B, C, D, E, only one correct answer. What is the probability that she answered both questions incorrectly? All right, so we know we're dealing with the multiplication rule because she'll be making 2 decisions in a sequence. So she'll answer one question and then move on and answer the next. And we'd like to know the probability she gets the first one incorrect and also the second one incorrect. All right, so I'm just going to make a note here that for each question, she's got 5 choices. And one of those is the correct answer. So that would mean the other 4 of them would be the wrong answer. I'm just doing correct, incorrect. So each question, there's a 1 in 5 chance of getting it correct and a 4 in 5 chance of getting it incorrect. All right, so we're going to look for the probability that both questions incorrect. So she guesses incorrectly on the first question and then answers incorrectly on the second question. All right, so these events will be independent of one another, meaning that the probability of being incorrect on the second question is not going to be impacted by what she picked for the first question. So the probability for every question will remain the same. So we just have to go one question at a time. All right, so probability the first question is incorrect 4 out of those 5 choices. And then multiplication rule, and then as she goes to the second question, she'll still have a probability of incorrect at 4 over 5. And then it says to express the answer in percent form. There's different ways you could type this on a calculator. I'm just typing it like I speak it. 4 over 5 times 4 divided by 5. And that is 0.64 or 64%. All right, number 10, we've got a spinner with 10 equally sized sections. 8 of them are yellow, 2 of them are red. The spinner is spun, and at the same time, a fair coin is tossed. What is the probability the spinner lands on yellow and the coin toss lands on heads? All right, so again, we know we're talking multiplication rule because we'll be doing 2 things in sequence. We'll be looking at our spinner. We want the probability it lands yellow. And then we'll consider the coin, and we want the probability that it lands heads. So these events are going to be independent again. What happens on the spinner will not affect probabilities of the coin. So we'll start with our spinner. So 8 out of 10, that's our chance of landing yellow. And then for the coin, landing heads, 1 side out of 2 is a head. So you can type it like I did on the last one, 8 divided by 10 times 1 divided by 2 is 0.4. Or if you prefer, you could multiply numerators, multiply denominators. You'll still do 8 over 20 is 0.4. So different ways you can type in your calculator. And again, we'll do percent. So move the decimal 2 places to the right, and that will be 40%. Okay, so let's take a look at number 11. We're going to move on to dependent events. So we have a key ring with 12 keys. 3 of them open the house door. You're going to select 2 keys. The first key will be selected at random, and then the second key will be selected at random from the remaining keys. So we're going to pick a key and not replace it. So all future probabilities will change if we start removing keys. And this is what creates dependent events. We'd like to know the probability that the first key opens the door and the second key does not. So let me just write down, we want the probability that the first one opens the door. And then when we go on and pick our second key, it doesn't. I'll just write doesn't. So the second one doesn't. All right, you can go right to your substitutions, or or if you want to sort of organize your work, as I've sometimes done in class, just going to make a little table over here. So I've got some keys that open this door, some don't, and I have a total of 12 keys. So I've got 12 keys, 3 open the door. So 12 minus 3 would be the other 9 don't. And I'm going to start and pick a key, and I want the chance it opens the door. So 3 out of those 12 keys open the door. All right, and then we have to say, given that I just picked my first key and it did open the door, I'm removing that key. So as I go on to pick another key, we have to say we already picked one of these 3 keys that opened the door. So there's not going to be 3 anymore. We've removed it. We'd be down to just 2 left that open the door. We'd still have 9 that don't. And because we removed a key, we'd no longer have 12 keys. We would be down to 11 keys. All right, so we've got, I've got 2 that open the door, 9 that don't, for a total of 11 keys. And we're ready to make our second choice. We want the probability the second one doesn't open the door. So 9 out of those remaining 11. All right, and you're welcome to type that in and check, but that will be 0.205. All right, number 12, we've got a university class with 30 students, 17 are business majors, 5 psych majors, 8 accounting majors. Each student has only one of these majors. The professor will select 2 students for a demonstration. The first student will be selected at random, and then the second student will be selected at random from the remaining students. So again, this is sampling without replacement. After we pick a student, they're removed from the mix, and then we'll pick our next student. And they'd like to find the probability that 2 business majors will be selected. So we want the probability of a business major first, and then another business major second. All right, you can go straight to substitutions, or again, if you'd like to organize it, I've got business, psychology, accounting majors for a total of 30 students. So 17 business, 5 psychology, 8 accounting, when you are ready to pick the first student. All right, so we want the probability of getting a business student, 17 out of 30. And then multiply. Now, as we go to pick the next student, we have to say, given that I already picked a student that was a business major, I don't get to pick them again. We remove them from the mix. I would no longer have 17 business majors. There'd just be 16 left. I'd still have 5 psychology and 8 accounting. And I picked a business major first, so there's no longer 30. We'd be down to a total of 29 students. Now, as I'm ready to make my second choice, I can see that 16 out of 29 are business students. Okay, I'll let you type that one in and check. That will be 0.313. All right, so we'll just do this idea of dependent events one more time. And this one is a research company surveyed 50 shoppers, each of who made one of these purchases today. We're going to pick 3 shoppers at random, one at a time, without replacement. We'll find the probability that the first 2 shoppers bought toys and the third purchased clothing. So we want the first person to have bought toys, and then our second pick also somebody that bought toys, and then our third pick somebody that bought clothing. All right, I think I'm going to just make my little table here again. I've got toys, clothing, electronics, a total of 50 people. So 25 bought toys, 9 bought clothing, 16 electronics. And we're going to start picking customers or shoppers. All right, so we want probability the shopper purchased toys, so 25 out of 50. And then, so we have to say, given that we just picked a customer that bought toys, we remove them, so sampling without replacement, So I kind of think of it, if 50 people were in the room and 25 bought toys, if you pick somebody that bought toys and they leave the room, there'd only be 24 people left in the room that did buy toys. We'd still have our 9 clothing buyers, our 16 electronic buyers, but our one person that bought toys left the room. So there's not 50 people, there's only 49 people in the room. And we're ready to make our second pick. So the probability now that somebody bought toys would be 24 out of those remaining 49. And then we're getting ready to make our third pick. So now we're going to say, given that we picked somebody first that bought toys, we picked somebody second that bought toys. Now we're down to just 23 people that bought toys. We have our 9 clothing, 16 electronics, and we'd be down to just 48 people after picking those first 2. All right, and finally clothing then, the probability of clothing 9 people out of 48. All right, I'll type this one in. And again, I'm just typing it like I say it, 25 divided by 50 times 24 divided by 49 times 9 divided by 48, and rounding to 3 places, 0.046. So if the table helps you, make a table. And if you're fine with just sort of keeping track on your own, then that's fine too. All right, and then our last question here, we're done with our multiplication rule. We're going to focus now on conditional probability. So I've got a city planner. They surveyed residents, and they're going to keep track of 2 pieces of information. So this is called a two-way frequency table. We're keeping track of whether the resident had a car or not, and whether the resident lived alone or not. So I'm just going to do some totals here. So in this survey, if you add those, 49 residents said they live alone, 122 said they did not live alone, and adding those gives us 171 people, 171 residents were included, but they also classified those 171 based on whether they own a car or not. So 60 own a car, the other 111 did not. And that gives us our total of 171. So those 171 people make up our sample space. So we'll be choosing one of them at random, and they'd like to find the probability that the person owns a car. So I am going to write the theoretical probability formula just because I want to compare it to parts B and C. So we're going to take the number in our study that had a car and divide it by the number in our sample space. So capital S there for our sample space. So I'm just going to focus on the denominator for a second. So we're going to consider all those 171 residents. And of those, there are 60 that owned a car. We're going to leave that as a fraction. So I want to compare that to B here. It starts the same way. It says, what is the probability that the resident owns a car? Oops, my screen is being glitchy. One moment. Well, my computer is being so temperamental today. I really don't want to stop right here. So let me see if I can get it going again. Come on, computer, you can do it. Maybe. All right, my table's a little crooked, but let's see if that works. All right, we want the probability that the resident owns a car. But now it says given that, so that vertical line, it's called a pipe on a keyboard. That vertical line is read given that, and this is called our condition. So given that the resident lives alone. So a given that statement restricts who you can consider. You're not allowed to consider all 171 residents. You can only consider those that meet the condition. So lives alone, whatever the condition is, whatever's after the given, this determines your new denominator. So I'm going to write the formula. For some people it helps, others can go straight to that answer. But what we'll do is we'll look at the number of residents that meet both conditions. They own a car and they're among the people that live alone. But our denominator, we're only going to be looking at the number that satisfy the condition of living alone. So essentially what's happening when it says, given that, you're restricting who you can look at to only the people that meet the condition. So I'm only allowed to look at the people that live alone. And that's why my denominator is not 171. My denominator is just going to be those 49 people that live alone. And then we can do probability. So if we're only looking at those 49, we want the probability the resident owns a car. So out of those 49, 9 of them also meet the condition of owning a car. All right. Oh, crazy computer. Try one more time to get it back in action. I'm very much not happy. All right. I really don't want to stop. Hold on one more second. All right, computer, you can do it. Here we go. So let's find C, the probability that a resident lives alone, given that they own a car. All right, so now the given condition there, this will determine our denominator. So our numerator will be the number that satisfy both conditions. They live alone and they have a car. But our denominator, we're only going to be considering people that own a car. So again, let me just focus on my denominator first. So the condition is have a car. So I'm just going to box in that row. So you're going to ignore the rest of the table. You're only allowed to look at those 60 residents that own a car. And then you can do probability. So probability that they live alone, if I'm only looking at these 60 people, so living alone would be 9 out of those 60. All right, and there you go. That's conditional probability and our page 2.